Okay, going back, we'll now talk about the convection. So convection is a transfer mode. Convection is a transfer mode that comprises of two mechanisms. The idea is this: as I have already said, that we have, let's say we have a plate right here, a surface, heated surface, let's say, and we have a moving fluid. So it's a heat transfer occurring because of the motion of the fluid in this on a surface, and it can actually be classified further as either forced convection or natural convection. Okay, so forced convection is just simply from the word force. There's some mechanical means, like let's say fans, blowers, or compressors, or pumps. If it's a fluid that's passing through a surface, and that fluid is actually the ones carrying the heat, right? So that's forced convection. But for natural convection, it's just simply because there's going to be difference in the densities. Once imagine that this is a heated plate, then once the fluid, or let's say the air, pass through that heated plate, or pass over that heated plate, it's going to be, some portion of the fluid will actually absorb that heat, or will carry that heat, and in a way it changes their densities. And because there's going to be changes in the densities, then there's going to be a motion, natural motion of the fluid or the air. Okay, so we have that motion, and we call that natural convection. Now there's also another sub-classification for convection, wherein I didn't include it here, and it's the heat transfer associated with change of phase. Okay, anyway, here's our equation for the convection heat transfer. So the heat flux, again, that's the watts per area, heat rate per unit area, is equal to H times the temperature difference. So you see, again, this is temperature difference, but the temperature difference is the temperature of the surface. This is the difference between the temperature of the surface and the temperature of the fluid. So it's not always Ts minus d theta. It can also be not d theta, like this, the d fluid. So sometimes if the heated air is, if the air has higher temperature than the surface, then that's gonna be the temperature of the fluid minus the temperature of the surface, right? So just take note that heat, go back again to our fundamental concepts, that heat travels, transfer from region of higher temperature to region of lower temperature. Okay, so you can just interchange the two. And this one, H, is what we call the convection heat transfer coefficient. So here it is, heat transfer coefficient. So the unit of this is watts per meter squared Kelvin. Right? So the difference between this and the thermal conductivity is that the thermal conductivity is watts per meter. In terms of unit, the difference is watts per meter per Kelvin, whereas this heat transfer coefficient is, or let me write it here. Okay, so the thermal conductivity is watts per meter Kelvin, whereas this one is watts per meter squared Kelvin, or yes, I think that's it. And this heat transfer coefficient is actually that depends upon a lot of factors, because there's a fluid motion, so that depends upon the type of fluid, and also the geometry of the conduit. Is it a flat plate? Is it a let's say, is it a curve? Is it a cylinder? So is it forced? Is it natural? So there's actually it actually affects the heat transfer. So this H value is a function of many other or is affected by many other factors. Okay, so that's actually the problem in convection heat transfer, because we are going to find this H. However, here in our topic number 1, there are sorry, this is not thermal conductivity, this is rather convection heat transfer coefficient of selected fluids, I guess. So we have air, and it says here we have 6 to 30, and if it's superheated, that's 30 to 200. If it's water, of course, convection. So it's actually a range, because it's affected by many factors, as I have said. So it also deals with, is the fluid in laminar flow, or is it in a turbulent flow? So that's the problem of heat convection. Okay, and the last mode is the radiation heat transfer. So as I've said, the radiation heat transfer is just simply because a body that has a temperature above 0 Kelvin, it actually emits and absorbs radiation. So if you see the radiations, I mean electromagnetic spectrum, there's actually the electromagnetic waves, and you can see that there are shorter waves, we have longer waves, and that actually corresponds as well to the energy. So shorter waves have much higher energy than this longer waves. And thermal radiation is just a portion of this electromagnetic portion, so it's not the entire thing, but rather this one. Okay, so if we just zoom in to some portion of the electromagnetic spectrum, let's say we have here 10 to the 8, that's the wavelength, right? This is the, I guess that's the unit, that's the wavelength. Alright, so if this is the wave, then what's going to be the wavelength? So from 10 to the negative 8 meters to 10 to the 8, so we just zoom in, and right here we have I think this is the radio waves. This is let's say, I guess this is X-rays, and this is gamma rays. Okay, and the thermal radiation is only in this range, right? Thermal radiation, and I just forgot the exact value of this wavelength, but this portion is actually comprised of ultraviolet waves and visible light. The electromagnetic waves portion of the visible from the visible light, and also some infrared portions. So this is what we call the scope of thermal radiations only. So we're not gonna talk about transmission of gamma rays or X-rays or radio waves. We're just gonna talk about the thermal radiations. So again, as I said, the thermal radiations, they just it's just present whenever the temperature of a body is above 0 Kelvin. So let's take, for example, we have this body right here, and we have pictures that it's actually emitting a lot of waves. So it can emit gamma rays, it can emit whatever waves, but again, we'll only consider waves coming from a thermal radiation. Okay, so the equation is actually from the Stefan Boltzmann Law. Alright, Stefan Boltzmann Law. This is one individual, Stefan, and another individual is Boltzmann. So the expression of thermal radiation is the heat flux is equal to the epsilon times this theta times the temperature to the fourth. So again, temperature is always present, and this theta right here, this is the Boltzmann constant, and this is equal to 5.6 567 times 10 to the negative 8. Okay, so you can't actually forget this because this is 5, 6, 7, and 8. So 5.67 times 10 to the negative 8. So that's the Boltzmann constant, and this epsilon is what we call the it's actually a radiative property of the surface. So does it emit everything? I mean, does it emit 100%, or does it emit only 30%, or does it absorb only some fractions? So that's why this epsilon is actually present. Now, for some ideal situations, this epsilon is equal to 1. Well, if this epsilon is equal to 1, then we call that body a block body. Okay, so again, when a body has an epsilon or has an emissivity of equal to 1, we refer to it as a block body. And what is a block body? A block body is a body which absorbs all energy. Again, absorbs all energy, or it emits reaches it and reflects nothing. So it's emit, again, a block body is a body which absorbs all energy, that reaches it and reflects nothing, or in other words, it's a perfect absorber, right? So from this definition, it absorbs everything and it also emits everything. Okay, so when we say absorbs, meaning that another energy is coming from another surface. Heat transfer, some heat is being emitted by another surface. So that's why, from this point of view, we are actually referring to two surfaces. So if this surface emits, then another surface also emits. Then from this point of view, it's absorbing this energy or this heat transfer, and from this point of view, it's absorbing this heat transfer. Okay, so if the epsilon is equal to 1, then we call that a block body. And take note, this is just a model or something like an ideal body, and it doesn't actually refer to the color. Okay, so this is a concept, a model concept of a perfect thermal radiator, that is a perfect absorber and perfect emitter. However, real objects, they don't they have emissivity that's actually less than 1. So right here in table 1-4, we have here, for example, an aluminum foil, it is 0.07, a polished stainless steel is 0.17, anodized aluminum is 0.82, a white paint or black paint is 0.98. So it's actually never 1.0, because 1.0 is just for idealized objects, or again, we use idealizations if we solve some heat transfer problems, but and sometimes we just assume that it's a block body. But if we have a given value of emissivity, or in some transfer problems that we need to consider this value, then we need to include that in the equation. Okay, so some radiation problems concerns to, again, this is just going back to this concept, we're in net heat exchange between two surfaces. So that's why this equation is sometimes expressed as in terms of this. So we have this epsilon, we have the Boltzmann constant, and we have this temperature raised to the 4th of the first surface and then another surface. So again, T sub 2 minus T sub 1. So one surface has higher temperature than the other. Okay, so right here is our figure 1-8. So net energy exchange between two surfaces. So let's say we have surface A, we have surface B, and this one is emitting thermal radiation. Surface B is also emitting thermal radiation, but one is higher than the other, then there's going to be a net exchange. So if A is greater than B, then of course the net exchange will be going to B. Okay, and here's our references. We have textbooks from popular textbooks in heat transfers. So we have hard copies for that as well. Alright, so now let's have a summary of the equations for the basic modes of heat transfer. So first we have conduction, and the second one is convection, and the third one is radiation, thermal radiation. Okay, now for the conduction, just recall the basic concept of these heat transfer, usually within the medium. So within the medium, and the equation that we have here is the heat flux is equal to negative K times delta T, the temperature difference, divided by the thickness, or the path, the length of path for the heat flow. Okay, this K is the thermal conductivity. This is thermal conductivity, and this is the temperature difference between 2 points, and the delta X is the length. Okay, what else? For convection, it's heat transfer usually, let's just write it here, usually between fluids, between a surface and a moving fluid. Okay, so that's the brief description, and the equation is the heat flux is just equal to H times Ts minus the temperature of the fluid. So again, it's not always the surface, the temperature of the surface minus the temperature of the fluid, because in some instances, or if the temperature of fluid is higher than the surface, then that's going to be the T of the fluid minus the T of the surface. And this one is the heat transfer coefficient. Okay, and radiation is usually emitted by body above 0 Kelvin, right? So that's the above absolute temperature. Zero absolute temperature. And what else? The equation is for the heat flux between net energy exchange between two surfaces. That's going to be epsilon times the Boltzmann constant and the difference of temperature to the fourth of first surface minus the temperature of the second surface. But just take note, this is to the fourth, and also take note about this, the units should be in absolute temperature scale. Absolute temperature scale. Okay, so what that means is this should be in Kelvin or Rankine. Right? So this one is emissivity, and this one is the Boltzmann constant. Okay, so the difference between this, the K, the H, and this emissivity is that the thermal conductivity is a property of material. The emissivity is also a property of material, but for H, the heat transfer coefficient for convection, this is actually a factor of, it's affected by many factors, like, for example, the type of fluid, the flow of fluid, if it is in laminar flow or if it is in turbulent flow, and as well as the geometry of the surface, if it is a cylinder, if it is a flat plate, or is it positioned vertical, or is it positioned along the horizontal. So there's a lot of factors. Okay, so now let's solve one one problem regarding conduction. Okay, so here's our first sample problem for this topic, and just recall that our working equations are just gonna be coming from the basic modes of heat transfer, and as well as sometimes you'll be getting equations from thermodynamics or fluid mechanics. Anyway, so here's the problem. This problem is taken from the textbook by Creeth et al., Heat Transfer Principles and Applications, and this is actually example 1.1. It says here that the wall of an industrial furnace is constructed from 0.15 meter thick fire clay brick having a thermal conductivity of 1.7 watts per meter Kelvin. Measurements made during steady state operation reveal temperature of 1400 and 1150 Kelvin at the inner and outer surfaces respectively. What is the rate of heat transfer or heat loss through a wall that is 0.5 meter by 1.2 meter on a side? Okay, so it's actually coming from an industrial furnace, and let's say here's our industrial furnace. Furnace, by the way, is something like a heat source or for heating applications. So it's the principle of operation is that there's actually biomass or fuel that's being burned inside the furnace, and because of the thermochemical reactions on the biomass, then there's gonna be heat that is being generated. Right, so we're just gonna take one portion, like let's say this portion or this side of wall wherein we have these dimensions, 0.15 the thickness and 1.2 by 0.5 meters. Okay, so it's actually a chamber, so something like a chamber. Okay, so for the solution, number one is to list down necessary information as usual. Right, so we have K of the material is 1.7 watts per meter Kelvin, and just take note of the heat transfer direction. So that means that this one, the 0.15, is the delta X. Okay, so delta X is 0.15 meters, and the T sub 1, of course, that's going to be the temperature coming from the rear surface, from the inside. So that's right, here's the inside surface, and here's the outside outer surface. Okay, so T sub 1 is our inside surface. The temperature is 1400 Kelvin, and the second temperature is 1150 Kelvins. And the area is the area that's perpendicular to the heat flow, and that's gonna be the 1.2 meter by 0.15 meter. Alright, so let's write it here, 0.5 meter by 1.2 meter. Okay, so now let's solve for the heat rate. Okay, take note, this is heat rate because we have the area, then we are going to solve for the heat rate. So heat rate is the Q dot is equal to negative Ka times delta T all over delta X. Now what is K? This is, alright, let's just write negative 1.7 watts per meter Kelvin times the area, this is 0.5 by 1.2 meters squared, right, times the temperature difference, we'll just write it here, times 1150 minus 1400, and here, this is in Kelvin, divided by the thickness 0.15 meters. And if you do the unit analysis, you'll see that this is Kelvin, right? Kelvin, or let me write this, negative 1.7 watts per meter Kelvin times 0.15 times 1.2 meters squared times 1150 minus 1400, right? That's in Kelvin divided by 0.15. Okay, so you'll see that we have a cancellation of the Kelvin term, and what else? We have a unit of meter here, right? So meter, and we have the meter squared. So what's left is the unit of watts, and you'll see this is a difference between a lower value and a higher value. So we have negative term that's coming from this from these terms, and times the negative, so we have a positive value. So if you do the math, what we get here is 1700 watts. Okay, and if we want to solve for the heat flux, so to solve for heat flux, you can just simply divide it by the area. So heat flux, Q divided by A, Q dot divided by A is equal to negative K delta T over delta X, or just simply this one, the heat flux, right? So you can divide this by area, or you can just start all over again from this conduction equation and do not include the area, and what you get is the heat flux is equal to 2833 watts per meter squared. Okay, so that's just a straightforward problem. In the next video, we will do another problem regarding this basic modes of heat transfer.